Okay, let's dive into a truly pivotal moment in theoretical physics. Picture this. A brilliant mind, Peter Higgs, grappling with these huge fundamental questions about the universe. He's facing skepticism, serious skepticism, and then finds a solution. But it's rooted somewhere really unexpected. The physics of superconductors.
Right, a field that many particle theorists back then just sort of dismissed, famously called, quote, another country.
Exactly. So our deep dive today is all about that fascinating story, the Higgs mechanism. We're leaning heavily on Higgs' own words from his 2013 Nobel Lecture, Evading the Goldstone Theorem.
Yeah, and what's so compelling here, I think, is that it's not just about one discovery. It's this confluence of ideas, challenges, and just sheer persistence. It really reshaped how we understand particle mass. And for those of you tuning in with a physics background, you'll definitely appreciate the nuances of the theoretical landscape Higgs was working in. It was tricky.
Absolutely. So our mission today is to explore the specific problem Higgs tackled, this thing called the Goldstone Theorem. And then we'll trace how his, well, ingenious solution really opened the door to the standard model as we know it now.
Culminating, of course, in predicting the particle that gives others mass, the Higgs boson itself.
Okay, so let's set the scene. It's 1960. Peter Higgs has just joined the University of Edinburgh. He talks about these early days, mentions a Scottish university summer school where people like Sheldon Glashow, future Nobel laureate, were debating theory.
Apparently sometimes helped along by hidden bottles of wine. Classic physicist behavior, maybe.
Perhaps. Though Higgs says he wasn't really in those specific late-night chats, but he was definitely hunting for a solid research direction. He was fascinated by symmetry, but really puzzled by what looked like approximate symmetries in particle physics. Why weren't they perfect?
And connecting that to the bigger picture, his early interest was actually quantum gravity. But he shifted towards particle physics, specifically symmetry. Then in 1961, he gets completely captivated by these papers from Nambu and Goldstone.
Ah, yes. Spontaneously broken symmetry.
Exactly. They introduced this idea where the underlying rules, the dynamics, are perfectly symmetric. But the reality we see, the ground state or vacuum, isn't. It's asymmetric.
Like that pencil standing on its tip analogy you mentioned before we started recording. Perfectly symmetrical, but it has to fall one way or another.
Precisely. The symmetry is hidden or broken in the outcome, even if it's there in the fundamental laws.
Okay, so this is a powerful idea. But Nambu's models, they drew inspiration from superconductivity theory, right? BCS theory.
That's right. Bardeen-Cooper-Schrieffer theory, based on Bose condensation of Cooper pairs of electrons. Goldstone also used ideas from condensed matter scalar fields, a wine bottle potential drawing from Ginzburg-Landau theory.
But here's the rub, isn't it? At the time, quantum field theory wasn't the go-to for strong and weak interactions.
Not at all. And condensed matter physics. Particle theorists often looked down on it, saw it as, well, completely separate. Less fundamental, maybe.
You mentioned Robert Brout recalling Victor Weisskopf's comment.
Yeah, back in 1960, Weisskopf apparently said particle physicists were so desperate these days that they have to borrow from the new things coming up in many body physics like BCS. Perhaps something will come of it.
Wow. Talk about skepticism. It really highlights that another country mentality, doesn't it? These intellectual silos.
It really does. It makes you wonder what breakthroughs we miss today because of similar thinking.
So why was there so much skepticism specifically about Nambu's approach, even though it showed promise?
It's a great question. Nambu had shown how breaking chiral symmetry could generate mass for protons and neutrons, which was, a big deal. But his model also predicted massless spin-narrow particles, pions, essentially.
And pions do have mass, that's the problem.
That's the first problem. And the second, as Steven Weinberg later pointed out, is that if they were massless, they'd radiate energy from stars like crazy. Completely contradicts what we observe.
Okay. And Goldstone's work seemed to double down on this issue.
It did. Goldstone argued that these massless particles were an inevitable consequence, arising from excitations around the minimum, the trough of that wine bottle potential. It seemed unavoidable.
Which brings us smack bang into the Goldstone Theorem.
Exactly.
Yeah.
1962, Goldstone, Salam, and Weinberg published Broken Symmetries. And the theorem they proved was pretty definitive. It stated essentially that in a relativistic quantum field theory with a continuous symmetry, if that symmetry is spontaneously broken,
then you must have massless, spinless particles.
Are the
Goldstone bosons.
Precisely, and that looked like a complete dead end for Nambu's program. How do you get massive particles without also getting these unwanted massless ones?
It seems like an impossible hurdle, so how did they get past it?
The first hint, the first crack in the wall, actually came back from condensed matter physics from Phil Anderson in 1963.
Ah, the connection comes full circle.
Kind of, yeah. Anderson pointed out that in a superconductor, this Goldstone mode doesn't stay massless. It actually combines with the electromagnetic field and becomes a massive excitation called a plasmon.
Okay, so it gains mass through interacting with something else.
Effectively, yes.
Yeah.
Through the long-range Coulomb forces.
Yeah.
And crucially, this massive plasmon provides the longitudinal component for the photon, which also becomes massive inside the superconductor.
The photon gets mass. That's weird.
Inside a superconductor, yes. Anderson famously quipped, "The Goldstone zero mass difficulty is not a serious one because we can probably cancel it off against an equal Yang-Mills zero mass problem."
So he saw a potential parallel in particle physics with Yang-Mills theories also predicting massless particles.
He did, but, and this is a big but, Anderson's work wasn't relativistic.
Ah. So particle theorists, including Higgs initially, didn't immediately see how to apply it.
Right. It was an insight from another country, and it wasn't framed in their language, the language of relativistic quantum field theory. So the problem wasn't quite solved yet. Others tried.
Yes. In March '64, Abe Klein and Ben Lee suggested maybe you could modify a key equation in the Goldstone Theorem proof, even relativistically, borrowing from condensed matter ideas.
But that didn't fly either.
Nope. Wally Gilbert shot that down just a few months later, in June, showed their modification violated Lorentz invariance, a fundamental principle you just can't break.
Okay, so Klein and Lee's path is blocked. And this is where Higgs comes back in strongly.
This is the moment. Higgs reads Gilbert's paper, ruling out Klein and Lee's idea on July 16, 1964. And he said he was upset.
Upset? Why upset?
Because he felt Gilbert was right about the specific issue with Klein and Lee's approach, but he still had this nagging feeling that the Goldstone theorem must have loopholes. There had to be a way.
And over that following weekend, something clicked.
Something clicked. He started remembering things he'd seen elsewhere, specifically apparent violations of Lorentz invariance in Julian Schwinger's work on QED, quantum electrodynamics.
Okay, hold on. Schwinger's work violated Lorentz invariance. I thought that was forbidden.
Ah, good point. It was an apparent violation. Schwinger liked using a particular mathematical setup, the Coulomb gauge, which looked non-relativistic on the surface, but everyone knew it was just a mathematical choice, a gauge choice, and the actual physical predictions were perfectly consistent with relativity. It didn't cause any real conflict.
Okay, so it looked wrong, but wasn't actually wrong. How did that help Higgs?
The crucial part was why Schwinger could do that and what else Schwinger had shown. As recently as 1962, Schwinger had published papers basically demolishing the common belief, the sort of folklore at the time.
The folklore that gauge invariance automatically means massless force carriers, like the photon.
Exactly that folklore. Schwinger showed examples where you could have a gauge theory with massive photons. He didn't spell out the mechanism causing the mass, but he showed it was possible in principle.
Wow. So Schwinger had laid some groundwork there without maybe realizing its full implication for the Goldstone problem.
Precisely. And during that weekend, July 18th, 19th, Higgs had his aha moment. He realized Schwinger's way of handling gauge theories actually undermined the basic assumptions, the axioms, used to prove the Goldstone theorem in the first place.
So the proof itself had limitations.
It relied on assumptions that didn't necessarily hold in these types of gauge theories. It suggested gauge theories weren't part of the problem, they were the solution. They were the way to evade the theorem.
Okay, that's huge. So he has the insight. What next? Did he write it up quickly?
Incredibly quickly. The following week, he wrote a short paper outlining this theoretical argument, sent it to Physics Letters on July 24th, and boom, accepted.
Wow. And then?
Then he immediately wrote a second paper. This one was more concrete, describing the simplest model he could think of to illustrate the idea.
What was the model?
He basically took Goldstone's simplest scalar model, the one with the wine bottle potential, and added electromagnetism, a gauge interaction. And in that model, it became crystal clear. The massless Goldstone mode wasn't there anymore. Instead, it combined with the photon. It essentially became the third polarization state, the longitudinal polarization, needed for a massive spin-1 particle. The photon effectively ate the Goldstone boson and became massive, just like Anderson had hinted at in superconductors.
Okay, a concrete example showing the mechanism. That must have been accepted immediately too, right?
You'd think so.
Yeah.
He sent it to Physics Letters on July 31st. and it was rejected.
Rejected after the first theoretical one was accepted? Why?
Yeah, quite the shock for him, I imagine. The editor apparently just suggested he develop the ideas further. Higgs was, understandably, indignant. A colleague later told him the word from CERN theorists was basically, "This has no relevance to particle physics." Strange, isn't it? The abstract paper gets in, the physical illustration gets bounced.
It is strange. Maybe too strange, too fast for the establishment.
Could be. It shows how new ideas, especially ones crossing disciplinary lines, can face resistance. It wasn't seen as mainstream particle theory yet.
So Higgs didn't give up.
Not at all. He revised the paper, added some remarks about possible physical consequences, and sent this new version to a different journal, Physical Review Letters.
And what was the key addition in that revision?
He added this crucial sentence. It is worth noting that an essential feature of this type of theory is the prediction of incomplete multiplets of scalar and vector bosons, meaning the theory predicts a specific kind of unusual pattern of massive spin-1 particles, vector bosons, and massive spin-0 particles, scalar boson, like the Higgs boson itself. It was a clear experimental signature to look for.
And this version was accepted?
Yes. Received August 31st and accepted. And right around then, Higgs found out about similar independent work by François Engler and Robert Brout. Their paper had actually been published the same day his revised paper was received.
Wow, talk about simultaneous discovery.
Incredible convergence. And later, Nambu revealed he'd refereed both the Higgs paper and the Engler-Brout paper. Small world.
So the mechanism now often called the Brout-Engler-Higgs mechanism, or just Higgs mechanism, was out there, along with work from Gralnick, Hagen, and Kibble around the same time. But did acceptance come quickly?
Oh, definitely not. It took time. Higgs himself talked about facing really skeptical audiences, like axiomatic field theorists at Princeton and Harvard in March 1966. These guys were still convinced the Goldstone Theorem was absolute, no exceptions possible. Even Shelley Glashow, whose own electroweak theory would eventually need this mechanism.
Yes.
Glashow apparently complimented Higgs, said it was a nice model, but didn't seem to connect it to his own work back then. The potential wasn't immediately obvious to everyone.
And initially, Higgs and the others thought it might apply to the strong force, right? The broken symmetries there.
That was the initial hope, yes. Applying it to the broken flavor symmetries of the strong interactions, but it just didn't work out. The predictions didn't match reality.
So if not the strong force, then where was the right application? How did it become central to the standard model and particle mass?
The crucial connection, the real breakthrough application, came in 1967 from Stephen Weinberg and independently Abdus Salam. They took this mechanism, this idea of spontaneous symmetry breaking in a gauge theory, and applied it brilliantly to the electroweak theory, the theory unifying electromagnetism and the weak nuclear force.
Okay, so they used it to explain the masses of the W and Z bosons, the carriers of the weak force, while keeping the photon massless.
Precisely. The underlying symmetry is broken by this pervasive field, the Higgs field, permeating all of space. Particles interact with this field.
Like moving through cosmic molasses, as the analogy goes.
Exactly. The more a particle interacts, the more inertia it gains, the heavier it effectively becomes. The W and Z interact strongly, they get heavy. The photon doesn't interact with it, it stays massless. It just elegantly explained the observed pattern.
But even then, the story wasn't quite complete, was it? There were still theoretical hurdles.
Right. A big one was, could you actually calculate things with this theory? Was it mathematically consistent? That's the question of renormalizability.
Renormalizability.
Right.
That means you can handle the infinities that pop up in calculations and still get sensible finite predictions.
You got it. Without it, the theory is basically useless for making precise predictions. And it took another 4 years, until 1971, for Gerard Hoof to prove that these types of gauge theories are renormalizable. A monumental achievement.
Okay, so the theory is mathematically sound. Then came experimental confirmation.
The next big step was in 1973 with the discovery of weak neutral currents at CERN. This was experimental evidence that favored the Glashow-Weinberg-Salam electroweak model over others.
So the pieces are falling into place. The theory works mathematically. Experimental hints support the framework.
And by 1976, people like John Ellis, Mary Kay Gaillard, and Dimitri Nanopoulos, also at CERN, were actively telling experimentalists, you need to look for the leftover particle from this mechanism.
The massive spinless boson predicted by the theory itself.
The Higgs boson. The hunt was officially on, though it would take decades, in the Large Hadron Collider to finally find it.
So we've taken quite a journey there. A deep dive into how Peter Higgs, drawing on ideas from superconductivity, gauge theory, wrestling with the Goldstone theorem.
Really helped pave the way for our entire understanding of mass in the Standard Model. Evading that theorem was key.
It really highlights how these breakthroughs often come from unexpected connections, and they almost always face skepticism, sometimes rejection, before becoming accepted wisdom.
Absolutely. It's a testament to persistence and the sometimes winding path of scientific progress. From a purely theoretical puzzle about symmetry and massless particles to predicting a fundamental particle decades before it could be found. Quite a story.
And that wraps up our deep dive for today.
You know, reflecting on that initial dismissal of condensed matter physics, that another country perspective, it really makes you wonder, doesn't it? What insights are we potentially missing today? What seemingly unrelated fields might hold the keys to the next big breakthroughs, whether in physics or completely different areas? Something to think about.